want to achieve with your class. I think that in the context of, say, MIT's syllabus, the role of 602X is that at the end, you can now do electronics. And if you happen to come in there and you knew electronics, good enough. I think that when I teach a class, I have a definition of what I need them to be able to do, or what I want them to be able to think, and the way I want them to think at the end of the class. So measuring, somehow setting the scale by where I start is, to some extent, missing the point. If I can get a class to the point where they can do what they need to do, isn't that sort of the objective?
Well,
it's like
okay.
Go with it.
Yeah, but for instance, when you have, so this gets back to like the whole question of how do you assess different schools when kids come into one school with way less skill than the other? Do you hold them to the same standard after 1 year of instruction? Okay, but I think there is a meaning of learning as change in knowledge, not just knowledge or skills or whatever. Okay, so the most obvious way to do this, now let's see if I can go back to here seamlessly, is simply to, whoops, is to give a pre and post test and see if there is an improvement, and what you actually might do is define, as people in this field do, the gain to be the difference between the score on the final one and the score on the initial one. Now, there's a question of whether you can give the same test before and after, or whether you would have to have two tests that are carefully intercalibrated the way the different SAT scores tests give you a scale, you know, from 200 to 800 that is based on your overall ability or overall skill, even though the questions were different. That's an important consideration, and they use a method that I will describe, given enough time, called item response theory, where they look at at each item, at each question, rather than at the test as a whole instrument. Okay, so if you give the same pre and post test instruction, then we only did that in ADMREV because most people who give MOOCs are in broadcast mode. And they don't care what's received, or they don't have a good way to measure what's received. So I'm going to talk about this is standard way of measuring the pre and post test, and that is to plot as a function of the pretest here, skill, the score on the pretest, you plot the gain, the difference between the post and the pretest. So if you learned everything, you'd be on this line. In other words, if you got, oops. Oh, now what has happened here? Oh, I've gotten in a different mode. Fact. Okay. Now what happened there? That's pretty crazy. All right. Okay. So if you got 90 on the pretest, the most you can gain is 10%, right? That's 100 on the post test. So this is a line where you would learn everything. Now, it turns out that many times what you see is that the students lie, the classes or the students lie on this line here with a normalized gain, that is to say the gain divided by the amount you could possibly learn of some constant number like 40.4 or 40%. In fact, there's a very large study of a huge number. Well, you can think of the gain, this little g, as being the fraction of what you didn't know before the course that you do know after the course. What fraction of what you didn't know did you learn? So here is the study that really put this on the map, especially as far as physics education is concerned, a study of 6,000 students in, 60 different courses. And what you see here is that the courses that were taught in the traditional lecture presentation, in other words, where the principal job of the teacher was to present information in a lecture or in a small class, that they're in the solid and colors, and then the reformed, in some way, active learning is in open. And as you can see from this, there is essentially a line here about 30%, where all the traditional courses lie below that line, and most of the interactive courses lie above that line. And this was true across, and these lines seem to be pretty straight, and this is, someplace like Harvard where the kids came in at 70%, and here is these squares here are high schools where the kids come in at 27% on a multiple choice test, where if they just guessed, they would probably get 20, I forget if it's, well, it probably has 5 alternatives, so they would get 20% if they didn't know anything. Okay, so now in our MOOC, how did we do? Okay, well, we got a normalized gain of 0.3, right on that line, and this was on the questions involving force, and then on the questions not involving force, we got a gain of 0.33, and they're essentially equal within error. So what we showed here is that there is learning in MOOCs, and that it is at least as much as in a traditional course. Okay. Caveat, 2 caveats. One, students in a MOOC are taking both the pre and the post test in an environment where they're able to look at other resources. Whereas usually in class, this is done, closed-minded. I mean, closed internet, closed book, which is really excellent preparation for the way life works. I mean, we really have to ask ourselves, when is the next time that an important thing in this person's life is going to be decided by their ability to answer questions without reference to the outside world, and figure out how we might adapt to that. But okay, so that's one caveat. And the other caveat is probably much more important, is about the affect. In introductory physics courses, 98% of the students are not going on in physics, and they are there to get their ticket punched. And the people in the MOOC are obviously there to learn because there's no reward, right, other than the learning. So that's a big difference too. Now there's a very significant thing about this study here, is, leaving that issue aside, MOOCs have been widely criticized as being great for the professionals that take them, but not being effective for people with less skill or less preparation or blah, 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 okay? So what you see here is that our MOOC was big enough that we were able to get data points for a lot of different classes. And so 1 and 2, there's the physics teachers, and reassuringly, they're actually the most informed to begin with. And back over here is 4, 9, and 6. 4 is that they don't have college calculus, but it's a calculus-based course. They may have high school calculus, but they don't have college calculus. 6 is they don't have a college-level physics course. And 9 is they have a high school education or less. And there's obviously no evidence that students, that those cohorts are learning less than anybody else. It may be that there is less retention of those students. I know that was true in the Colorado MOOC. I don't think it was seriously true in our MOOC, because over half of the students who finished the second assignment finished the course and got certificates. And I think that's a much better measure of attrition or persistence in a MOOC than the difference between the millions who come in and register, who may not, a third of them or a quarter of them won't even ever do anything in the course. It's much better. It's just like when I teach an elective course on campus. I know that the students are taking 2 or 3 courses for that elective slot they have left over. They're taking a couple courses the first week, and then they're going to decide the second week, and they're not really my students until they've handed in the second assignment. And so we see retention. From there on, we see retention rates above a half, and in the course that we taught specifically for teachers, 75% of the people who were satisfactory, who did a decent job on the second assignment, passed the course and got a certificate. Okay, my dean would be happy with that if it happened in an elective course on campus. If 75% of the students who passed in the second assignment passed the course with a C or better and didn't drop it or anything like that. Okay, so that's about what I want to say for those two cohorts. And now I want to mention a little bit about item response theory. I did before. And the idea of item response theory is that you can look at each item and independent of which questions are asked, you can determine a skill or an ability for the student. Yes, you had a question.
Yeah, I just want to take a step back about the pretest, posttest gain plots that you just showed, and challenge you to challenge the validity of the pretest and posttest questions as really measuring learning. Because you put up this grand question at the right at the beginning: how do we measure learning? And to what extent do you think are pretest and posttest questions flawed, or don't capture the whole picture of what we would like to capture as learning?
I never said they did. I just said, he said and I said, these are conceptual tests. And so the definition I mean, in physics, this was the tremendous revelation of the past 20 years of education research, was that students can solve a problem like a dump truck comes along, bangs into a sports car, and they stick together and they go sliding across the intersection, which has a coefficient of friction of 0.3. How far do they go given the initial speed of the dump truck and the mass is blah, blah, blah. Okay. We're not answering that kind of question. We're not asking that kind of question. And these concept tests, what we're asking is, did the force that the dump truck put on the sports car, was that greater than or equal to or less than the force that the sports car put on the dump truck, or can't you tell from the information given in the problem? That's a concept question.
Are these multiple choice questions?
Yes, they're all multiple choice.
Okay, so I have a question, which is, I teach a very large MOOC, I have lots of things. I always see gains on multiple choice tests just because the students are smart enough not to choose the same answer again. So how can you really measure learning in a situation like that?
Okay. Why did every single traditional course score less than 23% if the students are smart enough to learn the answers? That they only got 23% of what they didn't know on the pretest correct on the post-test. I mean, this is okay, I don't want to...
That's not an answer to my question.
Okay. There is some evidence and about...
Example, I could give you a true-false exam, and I'm confident you can make 100 out of the second try.
Okay, I'm confident I could give you a true-false question exam, and then 4 months later, I can give you the same exam, and you will not get 100%.
But we're not doing that.
That's the pre-post test. You give one at the beginning of the course and the other one at the end.
Tell me if what you're saying is that you're trying to have a pre and post test that are measuring the same concepts. It's not that you're repeating the same questions
No, we
verbatim.
repeat the same question. There's a lot of data that doesn't matter. We find a decay of about 2 weeks in giving a test, a weekly test, and then putting that question on the final. That's, okay, yes?
If you don't mind, I know you want to move on. So my background is actually in educational measurement, and I developed modeling, what I've been doing recently. So it's really interesting that you're talking about gain scores, which are part of this bigger family of growth measurement.
That's true.
And my question to you is about the gain score, which is recognizing the education measurement community is probably the least effective way to measure growth. However, all of the other ways are extremely complex, and most faculty are not likely to spend the time and possibly the money for the software to do them. Can you talk a little bit about the challenge to that? Or can you talk a little more about the different kinds of growth that there are, or the reasons for using gain score as the way to go? I mean, they're probably justifiable reasons for
Okay, fine. So I'm using grain score because it's widely accepted. It's, as you say, it's fairly straightforward to do, and it's interpretable in terms of a lot of other background, however flawed the method is. I personally think that the that the restriction to concept questions is more serious than any criticism of the method. And so now I'm actually going to talk about item response theory as a different way of measuring growth. First, I have to tell you what it is. It's basically sophisticated grading on a curve, and what you determine by pretty much a Bayesian method is the student's skill and how it fits on the Gaussian curve or the approximately Gaussian curve of the whole class. Now, and it actually extracts more information than the classical test. And we use it in two ways. As an alternative way to analyze the pre-post results, we just standardize the post-test IRT parameters, and then we use that to measure the skill at the pretest. Lots of the same criticisms apply. And then we used it to measure relative improvement, and I'll explain what, let's see, what's the next curve here? It doesn't have enough resolution. Oh, yes. This is the curve of showing the skill gain in standard deviations. And for those of you who know, you should get about 1 standard deviation in a normal class, and we're getting about 1/2 or a little less than 1/2. But I have to tell you that the effect size depends on the standard deviation of the class, and the MOOCs are twice as wide as our class at MIT. Or on the same scale, our class at MIT is 1/2 a standard deviation wide. And also 1 standard deviation below the average of the MOOCs. Okay, but the point here is that all the students in this class, in this MOOC, independent of their initial skill level, learned about this, had the same amount of skill gain. Okay, so I just want to emphasize that using either IRT pre-post testing or the standard normalized gain pre-post testing method, we come to the conclusion that, contrary to what a lot of opinions have been expressed about MOOCs, that we see that none of the various cohorts we studied showed significantly more or less gain than the others. The high school students versus those with advanced degrees, the people who had poor prerequisite preparation, or the students with low initial average skill. And so that's the take-home message from the pre-post testing. And this is actually an interesting figure. The blue is the overall class distribution. The yellow is the physics teachers, and just hopefully your kid is not in one of these guys' classes. And then the red is the MIT students who did about 70%, oh no, sorry, about 250 out of 408 of the same questions. And so you can see their skill is less, and you can see that the distribution is narrower. Now, we had in our course 408 questions, which is a lot. And so every week we have 40 questions. Now, most of the students, you have to get 60% right to pass. So most of the students didn't do all the questions, but they did a lot of them. And certainly with item response theory, we can get a valid skill each week for the students. Okay. Oh, this is not the curve I thought it was. Okay, so we can get the valid skill, and then here are the skills of several different cohorts. There is at the top here the physics teachers, then the people who had the MIT math-like background, and then the blue is not physics teachers, and these are our MIT students. And you know, I'd like to believe these are actually students at MIT who had failed the course in the fall and were taking it again in the spring. So they may have had a little bit extra skill here, so that may make this a little high. And of course, we may say it's going up at the end. But basically, we don't see a big effect from our interactive class, at least relative to the MOOC students. Just remember, though, that the MIT students are the students who've already failed this course once. They are not enthusiastic about actually learning this course. They just want to pass. Okay, so now let me switch over to MOOCs. Oh no, this is the relative improvement. So this shows the week-by-week skills of a particular student. And the student has, there are two kinds of data here. The solid points are the homework, and the asterisk points are the quizzes. And we see no difference between the homework and the quiz. But I have to tell you that the quiz was open course notes just the way, or open world, just the way the homework was. And also there was no time limit because the edX doesn't currently have, or at least didn't last summer, have a time test utility. And so, not too surprisingly, we don't see any difference between the quizzes and the homework. And we can throw them all together and do one least squares fit to them. And the derivative of this is telling us how that student is changing their relative skill, or their skill relative to all the other students in the class. So we're looking at the bell curve, and we're looking at it each week, so you can sort of think of it as bump, 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 bump. And then we're looking at students who start low and get high, or start high and get low. They would have positive or negative relative improvement. And this gives us another measure of growth. So I just want to show you the diagrams of where students spend their time in these courses. And this is relevant because it has to do with what resources there are in the course. Now, 8MREV, our physics review course, has, well, problems up at the top right, checkpoint questions, which are intermixed. It's based on an e-text. It's not a video course. This was really designed to be blended with our on-campus intensive problem-solving in groups classroom, the flipped classroom, I guess you call it now. And this was the material that we designed to prepare them for that class, and also to do some of the homework. And so you can say this 55, oh yeah, and then there's the e-text, and then there's the time that they spent in the discussion. And actually, the way that they actually work is that the students, when they're doing homework problems, they go to the discussion if they're stuck. And so the way we record the time is probably not the way that I think as a teacher you would normally record the time. What I mean by that is a student is here, student opens the problem, they have a homework problem, they can't do it, they open their book and they read some in the book, and then they discuss a little bit with their colleagues, and then they come back and they answer the question. We charge all the time that between when they read the book and when they went to the discussion group as book time, as e-text time, and all the time between when they went to the discussion and when they come back having answered the question as discussion time, even though they may have spent a large fraction of that after they went to the discussion actually working up a solution on a piece of paper. So this underestimates the amount of time that they spend actually doing problems or answering checkpoint questions. If you just threw in the discussion, you'd probably have a good approximation to the fraction of time that is spent on assessment activities. And now, in 6002X, it's a standard course in the sense that it is a on-campus course, traditional on-campus course, put online. It has a lot of resources. It has the primary instructional medium that is used by the students is the lecture videos. There is the discussion, and then in warm colors as before, there's the homework, the lab, and the lecture problems, the problems that are intermixed with the lecture. It also has a textbook, and it has a tutorial, as well as the discussions. Okay. So now, let's see. Okay, so now another discussion. One of the great things that has drawn me to orient my research group towards, away from the homework tutor mastering physics, that was our first big effort, and towards the MOOC, is the possibility that in the MOOC we have almost a complete snapshot, a record of what the students do, not only, not only just what they're due, not just the problems, but the discussions that they have, the particular discussions that they have, how much time they spent on the e-text, which page they read associated with which problem. I mean, if we wanted on campus to determine how long student Armando here spent on, while he was doing problem 3, in his textbook on page 237, I can't imagine any way of determining that wouldn't be considered highly intrusive. We put a little camera in his room, monitoring everything that he does. That's what we'd have to do. But in the MOOC, we have the data. And the students in the on-campus environment, the students have office hours, they have study groups, they have upperclassmen who are majors in that topic, and they can get help from all those, and we can't monitor that, again, without being extremely intrusive. But in the MOOC, we can see all that. And so my question to you is, what student activities, which use of these resources do you think correlates with skill or with learning? So I'll just go back here and show you the typical thing. Okay, what do you think students do who learn in the course by our definition, either the pre-post test or the week-to-week improvement relative to their peers?
Problems.
Problems and problems.
Getting tested.
What?
Getting tested.
Getting tested. Well, is homework, okay, is homework,
Mistakes method counts for something.
sorry, we were both talking at once. Is doing homework getting tested?
If they need to do a good job on it to pass the course, sure.
Okay, that's what they do. They have to get the right answer.
So methodological question and Dave?
Yes.
Methodological question and answering what will the week-to-week say. So as you said with the IRT analysis, it's sort of grading on a curve where the average performance is like a theta 0. So if everyone benefits from discussion, that is, everyone learns equally, won't it show that there's no learning week to week?
Yes, that's right. The relative improvement, I mean, we know from the pre-post testing that the tide is coming up, but the relative position relative to the water level can stay the same, and you're still learning, right? But yes, that's right. But methodologically, there still is, some activities are more effective, better use of your time, others not so effective. I mean, which of those do you think will correlate with learning? I mean, maybe you could just say the total amount of time you spend, right? Okay, so doing problems was one thing.
So I guess what I'm wondering about the correlations is how do you, in your analysis, account for the fact that students get to choose which activities they participate in? So the students who participate in the discussion, for example, might be very different students than the ones who didn't. And so then what you see as a correlation with discussion might really just be that that subset of students for whatever reason are different. Same with the problems.
Yes, so you have come to a critique, what I regard as a critique of this line of research, okay? What we're going to do is look for something that the students who do that get better, learn more, okay? And so we've agreed what learning is, and we can agree that this cohort, these students who have these characteristics in terms of how they spend their time or whatever, they learn more. Now, what we haven't established is that if applied as a treatment in an A-B kind of experiment would in fact cause the other students who chose not to behave that way to learn more as well. Okay, and this is, I totally accept that, and I just told you the next item on the agenda, which is to do, this summer we're doing A-B experiments where different instructional things are being applied. Okay, but still, okay, so we have doing problems. Gee, I mean, around here, the faculty are so concerned that the students read the book, and that they read the book before they come to class. Nobody said read the book. Okay. Yeah, okay, maybe a couple of people think that would be good. Yes?
From my limited MOOC experience, I would guess discussion.
You would, I'm sorry,
I would guess that participating in the discussion actually.
participating in discussion would be good. Okay, so we also have, all right, so I'll show you the results. It's interesting that, okay, I think implicit in this whole thing was that the time on task would be a measure, right? You spend more time, you're going to learn more. Secondly, do you think initial learning, maybe if you know more, if you believe in constructivism, if you know more when you come in, you should learn more. That is, in fact, it troubled me for a long time that the normalized gain was a constant. Why is the normalized gain a measure that seems to be constant across a lot of different classes or across a lot of individuals in one class? Why should everybody learn a constant fraction of what they don't know? Especially if you believe in constructive theories of learning, you would think that the students who have a higher initial skill would have more reference points to tie the new stuff in on. In fact, we published a sort of mathematical model, very crude, of memory learning, and the memory learning, and then of constructive learning, and the memory learning was simply defined as the amount, the probability that when you're exposed to something new, you learn it, is independent of everything else, just certain memory works a certain fraction of the time. And the other model is that your chance of remembering it is proportional to how much you already know, to your pretest score. And so the memory model gives constant normalized gain. And I'll explain to you very simply why that is. I am a bar graph. And this is the pretest. And the white here is what I know. And the orange here is what I don't know. And now I go to a lecture, and the teacher loads up a lot of knowledge nuggets in a cannon and blasts it at the class, right? That's the lecture. And the cannon is filled with little paint balls, and the paint balls are white. Okay, so now when the paint balls land on my pants, except on the dirty spots, then it doesn't matter. But when they land on the top, on my unknown, then they cover up a certain fraction of that, right? Because if I have, if I pull my shirt tails out and have more space, then these guys will increase my knowledge on the post-test. And it turns out that is the model, the memory-based model fits constant normalized gain. I'm not saying that in fact students are learning by memory when they do better on these concept tests, but I do have that suspicion because there's not a lot of research that shows that doing better on the concept tests is correlated with doing better in the standard end of chapter type problems. In fact, if you look in Eric Mazur's book on peer instruction, he has one graph where there's clearly essentially no correlation, another graph showing somewhat positive correlation. Okay, it could be initial knowledge, it could be study habits. Nobody mentioned study habits. You know, there's all the learning research that shows that you can learn more if you learn better if you spread out rather than just cram in before the test or before whatever. Okay, so let me just get on to the data here. So I'm going to look at weekly correlation, weekly improvement in gain, and I'm also going to look at gain both. So these are two separate things, and just start off correlating them with the time spent on these various activities. And so I'm going to get a lot of data presented to you, and I'm going to visualize it as follows. You know, you start here from 0, and if you have positive gain, you go around clockwise and you color that in blue. And if you have a negative correlation coefficient, you go around counterclockwise and you color that in red. Yeah, okay. So now I'll show you. Well, just remember, here's 8 MREV. There's the e-text, there's the discussion, there's the problems, there's the checkpoint questions, and that's it. Okay, so now here is the gain on the top line, the pre-post test gain. And then here are the various activities, the checkpoint questions, the discussion, the e-text, the problems, and the total amount of time. And for the pre-test, post-test gain, all of these things correlate positively with coefficients 0.2, 0.25, which means that we're explaining something like 6% of the variance, which is not very good. In mastering physics, where we had a much more tutorial type interaction with the students, on the MIT final exam, the correlation was about a half. Okay. So now we looked at two variables here that are closely related, the average skill that the student had and the initial skill. And you see that there's correlation across the board there. And then we looked at the relative improvement, and that is the improvement measured with IRT on all the questions in the homework and in the quiz each week. And some of those questions, a significant fraction of those questions, are basically concept questions, maybe 30%, but most of them are analytic answers or the multiple choice of analytic or symbolic answers. And so this is the result. It's not as dramatic as I would hoped. I would like to see that really reading the e-text didn't help at all. And getting, maybe doing the problems or doing just these checkpoint questions in the e-text worked better. I would say that it looks as if the checkpoint questions here, if you look at each column, the most positive one, the one with the most positive correlations is the checkpoint questions. And I don't know if that's an artifact of the way we measure or if that is actually the best use of students' time, because it means they're reading the textbook more interactively. Okay, so now let me go on and do the same thing for, show you the data for the division of time among the various resources of 6002X. And remembering there's the homework and then there's the lab. The lab was an authentic circuit simulator activity, and you had to design a circuit that would do such and so a thing. Okay, and then there's a discussion in the lecture video and so on. So here's the result. You see a lot of red there.
Since the categories aren't exact.
Yes. The lecture questions are like the checkpoint questions. They're short questions interspersed in the lectures. Okay. Well, I was actually pretty blown away by this. We're seeing correlation coefficients approaching a half, but they're negative. Okay, so now, so let's just take a look at those. Here we have these biggest two here, negative correlations, with the homework and with the lab. What this says is that the more time you spend on homework, the more time you spend in this authentic activity lab, the lower is your skill. Happy with that?
Yeah, because you're finding it difficult.
Okay, so now, what do you think is happening?
The other causation, if you are having difficulty with your skill, it takes you longer to do the homework.
Absolutely. In all the work before that we've done, we see very strong positive correlation between time on mastering physics or time on whatever, and higher skill. Okay? In this particular case, in a MOOC, you have this tremendously wide distribution of initial skills. And the certificates are given to people who earn more than 60% credit. And if you're a professional electrical engineer, you can go in there and you can solve these circuit problems quickly. In fact, they actually earned a little bit more score. It's interesting that the score here, you just pile up the points. It helps to watch the video because then you do the lecture questions, so these are highly correlated, and it helps to do the tutorials as well. But that's for total score in the course. And the reason is the tutorials were very much oriented towards helping you do the homework problems. Okay, so I think that we understand why students who spent more time on the homework have higher skill. I'm still upset by this line here. If we look at the relative improvement, well, we don't see much correlation between relative improvement and what students do, how they spend their time. But those correlations that are colored are statistically significant. And it's pretty clear there are a number of negative correlations that are statistically significant. So we're saying that there's a negative correlation between how much you learn and how much time you spend, or how much you learn relative to your peers and the time you spend, or that, I mean, you can think of the correlation either way. It's just A and B are correlated. You don't know if A causes B or B causes A or C causes both A and B. So I don't have a ready explanation for this, and maybe somebody does. Chris, are you?
Yeah, so the different cohort analysis you only did for 8M rev. I mean,
That's right.
maybe you would find that the normalized gain was a lot less for the weaker cohorts in this course. And they spent a lot more time and they didn't improve.
Yeah. So right, we have not done exactly the same research in these two courses. And so we don't know in the 6002X about the different cohorts. And unfortunately, a lot of the sampling survey data at 6002X was done, it's just called matrix sampling, where you only sample 10% of the kids. I mean, if you have 10,000 people in your class and you want to find out what fraction of them come from India, you don't have to ask all 1,000 to get a pretty darn, all 10,000, you can just ask 1,000. Well, that's great. But if you want to do these kind of correlations, then just having a tenth of your class know what country they come from or what cohort they're in, that's pretty bad. And then maybe it's a combination of two different cohorts, and then it's only 1% that you've asked. And so, anyway, so that's part of the reason we haven't done that research. And the other reason is because, we don't have a very big group. And the way that edX works now, you need to have a data miner to actually get the data out and really make sense of it, and then you need to have a psychometrician to do the IRT and other stuff, and then you need to have a learning person to run the MOOC and to put in the A/B test, and we're just a little bit thin. But we're hanging in there. So I don't really know. I don't know why there are these negative correlations between the relative improvement and the time spent. Yes?
Do you know the correlation, just in general, not any specific thing, between relative improvement and initial performance? Because I'd expect that there would be a negative correlation between those, sort of by definition. If you start at the very right of the bell curve, it's really hard to move farther to the right. So,
Okay. Okay. So you're getting at a big issue in a lot of these things, which is what is it called? A regression towards the mean. And we compensate pretty much for regression towards the mean because we look all the way across the whole course and we look at the slope. There still can be some noise in that affects you, but it's not as bad as just giving one pretest and then looking later. But these are pretty small coefficients, so it's conceivable that that's, I mean, I'm just skeptical when you do a correlation and it's 0.07. It may be statistically significant, but there can be so many other cofactors that I don't believe it. When I see 0.45 or 0.25, well, there's something there. Yes. Oops. No, I didn't do that. Somebody else did.
Have you run these statistics on any other courses? i.e., are these results content specific? Or because I think the question we're trying to ask is, does the intervention of a MOOC create learning, however we're defining that, in its participants? And so my question is whether or not this is specific to your domain or if it's transferable across all of the different MOOCs.
Oh, I think there's a big difference between the different MOOCs. And I mean, why in 6002X do we see so many negative correlations, negative 0.45? If you look at the same place in 8 MREV, you see plus 0.25, plus 0.25. That's a pretty big difference. We don't know. Maybe we were more successful in 8 MREV at restricting the skill of the students. I mean, there's just so many factors that I don't know. Yes?
I think your question points, a MOOC is not a MOOC is not a MOOC. I mean, there's good courses and bad courses. There's good homework questions and bad homework questions. There's good of all of that stuff. So just to say that it becomes very difficult to compare between courses because they're just, unless you're controlling for the instructional design and you're confident that they're all created to a similar level.
Right, so
You've
then
got too many confounding variables.
So at the risk of being blown out of the auditorium, I would suggest that we're actually asking sort of incorrect questions, right? Which is, it's not necessarily about the MOOC per se. It's not about an open educational resource. There's already data about, right? It's really about how we're using the tool and how do we measure learning. So for instance, I actually live in a professional environment and teach teachers to teach in a medical setting. And so to me, my outcome measures are, does their behavior change around information? Meaning, if they participate in this MOOC, or if they participate in an online educational experience, will their practice patterns change? Will their behaviors change?
Yep.
And so then you can use sort of downstream assessments, and it's not necessarily how much time they spent on the video in the MOOC that will provide evidence of what they learned.
Do you have a question? Come.
By the positive correlation between the video and the lecture questions, and it reminded me of an article in the Times that summarized some research by Henry Roediger. He's a psychologist.
That's the article showing that the testing is a very effective way of review.
Very ongoing, regular testing because it forces people to practice memory retrieval, so that you can. It explains why if you just spend a lot of time on the homework, you're not going to get anywhere. But also to build on what this commenter just said, it makes me wonder if the lecture questions were not well tied to the homework questions. So they're learning a lot by watching the video and having these ongoing regular assessments, which is something that the technology really lends itself to well. But then why they're doing poorly on the homework? Like were the lecture questions not preparing them well for the homework? I don't know. I'm just curious about the success in one area and following.
Yeah, I mean, I think that the implicit message of the Roediger paper is that you do better to keep putting all these questions within the e-text or within the video. And I think the MOOCs are using decent pedagogy in that respect. But largely, I feel that most MOOCs are digitizing the dinosaur. They're starting by digitizing the dinosaur of lecture-based education. And I call it a dinosaur because most education people agree that lectures are a very ineffective use of students' time and that there are many interventions that are better. And the Hake study is one of the classic studies to show that. Yeah.
First of all, did you offer the same MOOC more than once so that you could compare the same MOOC with different potential audiences? In other words, I'm fairly sure that the randomization of the audience of these things.
Okay, I agree with you, and we're torn between going back to later versions of 6002X and waiting to the end of this summer when we have our second MOOC that's similar to one last summer. Okay, I don't have any time left, but I want to show you what really converted me to believing in a lot of this education stuff. Look, okay. You know, I started this like anybody else who's a very popular, well-respected teacher, thinking that I knew how to teach. And so I made Mastering Physics, and I learned that okay, well, I'll tell you what I learned. It's a lot like quantum mechanics, where I am an expert. And in quantum mechanics, one of the lessons is that there is no reality until you measure it, and that your measurement affects the result. And I would say that's true in education. It's only worse. Okay. Okay, so what really, one of the big things that we did was to show how deleterious copying your master in physics was in terms of your final exam grade. Negative 0.47 correlation, blah, blah, blah. And then we looked under the hood, and we looked at the two kinds of questions on the final exam, the symbolic questions and the conceptual questions. And what we plotted here is and we could measure the amount of symbolic homework that was copied. And just about all the students did the early questions, which were the concept questions on the homework assignment. And so we actually got a normalized gain of around 0.38, which is pretty good, but I think it's because of the interactive nature of mastering physics. Okay. But now, here's the problem. Here's the problem. If we look as a physics teacher, we have expectations. The students start symbolic problems by conceptual reasoning, right? You figure out what physics principles apply, and then you write down the equations. Now, this conceptual test here, this orange line, orange fit, that test had about 40% numerical questions on it. Physics problems that, you hold the swing up here and you let it go, how fast is it going at the bottom? Well, we teach students, we teach students to solve the thing symbolically and then plug in the numbers. If you did that, you'd be a lot better at answering the numerical questions. And yet there is no correlation here, and there is a tremendous correlation here on the symbolic problems. This is 2.4 standard deviations. This effect size is 2.4 from this one intervention, namely doing your mastering physics homework. Okay, so now I just really have thought about this a lot. The problems cover the same topics, and so this is by the normal physics expert physicist who is also a teacher, unexpected. And I really think it gets back to the comment made about assessment. The students are not experts, and basically, I think we're only teaching them to answer our examinations, at least in these service courses. And I don't like that conclusion, but I'm pretty much driven to it. And that's the end of my talk. Cool. And I guess we have a couple minutes for discussion. So
Sorry, I actually think that we are already in lunchtime, and sorry. Dave is here. You can come and ask him questions offline, but we have already started serving lunch outside.
Okay. Yeah.
Sure. 12.